Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to solve a problem looking at center of mass. It might not look like it, but it's using torque to kind of look at the efficiency of the system. Now, the question's asking us that we want to lift this box over here. It weighs a certain amount of weight, and we want to lift it with only a certain amount of force. So we want to know where to place that peg to where this force will, be the easiest. We'll be able to apply this force, and it'll be the easiest to lift this box. Well, we know that wherever we place this peg, we want to know where to place that peg in order to rotate this thing, right? Make this more efficient. We know that wherever we place this peg will be the center of mass. Well, why is that important? Well, the center of mass is where objects naturally rotate. So for systems like this, if we place the point of rotation, or this peg, this thing's going to kind of go, right? It's going to wobble up and let's do this with, right? If this thing were to move, this thing's going to move back and forth. It's going to rotate around that peg, right? Systems rotate easiest around the center of mass, so we know that peg needs to be, in order for that peg to also be efficient, it needs to be in the center of mass. So we're kind of doing two things at once here, okay? Now we're told the weight and the force here, and we're also told the length of the plank that we're using in order to lift this weight. So the first thing we want to do is kind of draw a free body diagram. And again, the peg is also applying a force to this plank, but since we want the axis of rotation there, we're gonna kind of ignore that force in terms of torque, or we're gonna say that force doesn't cause any torque based off where that peg is, and kind of use torque to solve for where this position should be based off these two forces. So we draw our free body diagram, right? We know the force from the peg is going up. The force when I push down on this is going to go down. But we also know that the weight, even though this thing's lifting up, the weight of the object, the force of this object is down. Or the force that it's applying to this plank is going to be its weight, which will also be down. So we're left with a free body diagram like this, where this will be our center of mass, or no torque will be associated with that force, or since it's at the axis of rotation, our R is 0. And these two forces are the only two that are left. And so using torque, right, we build two torque equations for each force. The applied force needs its own torque equation, and since these are both perpendicular, we know we're going to use the torque equation that's associated with the perpendicular force, which we know is F(r) perpendicular. Since these are already perpendicular, we know the generic way to write these equations. For the applied force, R is going to be equal to what we call X. We could have called this X minus L too. And the point from the peg to mg will be just X minus L. So whatever this is minus this L will be the remainder of that distance, right? So we mathematically want to set up our R's, or distances from the force to the axis of rotation, in terms of X. So that's going to be one number, and we'll call that X. And this is going to be another number, which is this X minus this L. So these end up being our R's. So for FA, R is X. For FMG, R is going to be equal to X minus L. Okay, so when we write the torque equations for them, the torque for the FA, and since this is going to rotate this force is going to make it rotate in a clockwise motion, it's going to be positive, and then R is going to be X, and then times F, which F is FA. I should have put that in there. All right, and then for the torque for weight, since this force is going to make it rotate clockwise, which is going to be negative. Torque is going to be negative, and then R is going to be X minus L, and then F is going to be mg. So these are two torque equations. Now what we want to do is we want to assume that this is in equilibrium right now. So we want to sum these torques using Newton's first law. Because whether it's sitting still or I've lifted, right, I've applied this force and lifted the box up, in any of those positions, it's going to be the torque, everything's going to be in equilibrium. The thing will be moving, right? If I apply the force and I hold it there and hold the box up in the air, the system's in equilibrium. Just like if I don't hold on the box and the box applies force down, right? So this one would be tilted here. Either way, it would be in equilibrium. The only time it wouldn't be is during the press, as the box lifts up, but we don't want to look at that point. We just want to look at the point of either when the box is up all the way or when the box is sitting on the ground. In either of those cases, the net torque will be equal to 0. When the box is lifted all the way up, that is the better one to look at because that's where we'll have both these forces. So you don't want to look at, I know I said to look at the box on the ground, but what you want to do is you want to look at this system. So when we write this, I just want to make sure you understand why we're writing torque in terms of equilibrium. We're now saying that the box, right, we've applied the force, everything's in equilibrium. The box now is up in the air, and I'm applying the force over here, okay? So when we get to this point, once I've applied the force and I'm pulling the box there, we're in equilibrium. So we want to net those torques this way. So we take the torque from the applied force, right? And we start with that one, right? And then we know that torque for mg is going to be negative, so minus torque from mg. That's going to be equal to 0. And then what we do is we fill in this equation. So torque for the applied force is equal to x minus Fa, or x times Fa. Sorry about that. And then we know the torque for the weight is x minus L times mg, right? Again, it's right there. So we're just replacing that in there and replacing that in there and getting this equation. And we make it equal to 0. And then what we want to do is we want to multiply mg into both those places because we're going to need to factor x out. So we want to get x by itself. In order to do that, we have to first multiply mg in by L and by x, and we get this equation. So we end up with x Fa, which hasn't changed, but since we've multiplied mg in, we now get x times mg and L times mg. Mg times x, mg times L. Once we get that, we want to add mgl over to one side, leaving the x Fa minus x mg on one side here. Make sure you can see these steps. Right, on one side here and the mgl on this side. And then what I want to do is I want to factor out x. Since x is in both these terms, I can factor it out, leaving Fa minus mg inside. And then I can solve this for x, right, which would be mgl, right, where L is the original length we were given. We know mg, right, we know g, we know the mass of the thing, over the force, the applied force, which we know minus mg. That's going to be x. So when we're asked this question, where to place the peg, right, we could say, okay, well, x is going to be how far from the applied force, or you could take x and subtract it from L, and you could say the peg's going to be that far from the weight we're trying to lift. So either way, right, what you do is you take this x and then you apply it to your picture. You say, okay, where's this peg supposed to be? Well, from the applied force, it's going to be this distance, the one that I solved for. If it's from the object I'm trying to lift, then it's this distance I solved for minus the entire length of the plank. All right? So I hope that was helpful. If you have any questions about it, again, go back and rewatch. Again, the idea here is that we use torque, right? Because when we do lift this thing will be rotating, right? We use torque to find out where we place that peg, where that peg is essentially at the center of mass for the system. All right? Well, I hope this was helpful. Like I said, watch it a few times, and I will see you on the next video.